Okay, for today, we are starting with cosine of 5 pi over 4. Tell me one reason you know this is not an inverse trig question. Yes? Doesn't have the little -1. Okay, there could have, if this was an inverse trig question, it could have been like that. All right. What's another way you could say inverse that isn't using little -1? Yes. Yes, if you had written it a different way, cosine of theta equals something, then that's how you do an inverse, but it wouldn't have been written that way to start with. What's another way it could have been written to start with? Yes? That's a very good point, but that's not the question. What's another way to write an inverse besides a little -1? Maybe you missed this. Arc. A-R-C. Arc. Arc cosine. That would also have made it an inverse trig question. But this was, I told you, it was not an inverse trig question. And you said something impertinent that was very, very good observation. We're down here right now to do 5 pi over 4, because that's where that is. Why could this not possibly be an inverse trig question? Because it's in the third quadrant, and that's the dead zone. For inverse trig, you can't do stuff in there. All right, good. So this is different than what we used to do, but it is related. It's related to this. Okay, so let's finish this one off. Cosine of 5 pi over, that makes this a pi over 4, aka 45. And if that's a 45, this is the 1, 1, root 2 triangle. And then what's the most common mistake in circle trig? Negatives. And then, final answer is what? What do we even want? We have an angle here, so we want a side ratios. That's another reason this can't be an inverse trig question. Because when you're doing an inverse trig question, you're always trying to find the what? The angle. All right, and we're trying to find side ratios. All right, cosine, adjacent over hypotenuse. Adjacent, hypotenuse, -1 over root 2. Raise your hand if you had that one right. Okay, good, that's a good sign. Now, let's do one that's actually an inverse trig question. Inverse tan of 1/2, but wait, it's nested, and they want the cosine of that. Now, I know some of you are going to go, wait a minute, Mr. Server, we don't have the, that's not one of the triangles I memorized. It's okay. As long as you can draw me a triangle with all 3 sides. Yes, you'll have to figure out what the third side is. You can find the cosine of it. I know, this is not a 30, 60, 90 or a 45, 45, 90, but it doesn't need to be. My first step that I've told you is please rewrite this. Tangent of an angle is 1/2. But then realize there are some restrictions. Because this is an inverse tan question, do you remember the deal where tangents only allowed here and here? And so these are out? How many of you guys remembered that in the process of this? That's a good thing. So because it's an inverse tan, it had to be on the right side. And then of those 2 spots, which one must it be? Quadrant 1 or quadrant 4? Quadrant 1. Because, why? Because tangent is positive here, but it's not positive here. So that had to be out. All right, so then I'm here, and then I'm making my sides. Tangent, TOA, opposite over adjacent. 1, 2, and, square root of 3? No. What is it? Square root of what? Square root of 5. How do we get that? It's just this squared plus that squared. Okay, so 1, 2 square root of 5 triangle. Weren't these asking to find an angle? Yes, but the weird thing is I don't even need to know what that angle is, because all I really want for the end of the question is, what's cosine of that angle? So now I just do cosine on this triangle that I have right here. Cosine is adjacent over hypotenuse. You should have had an answer of 2 over root 5. Be honest. Maybe you had that perfectly right. 2 over square root of 5. All right, about 2/3 of the class. I want to try one more that's similar, maybe a slightly more challenging to challenge those of you that did get it right. We're going to go inverse cosine of root 3 over 2, and then I'm going to do the tangent of that. There's like 6 steps. People wonder why pre-calc is so hard. Pre-calc is hard because it's just got, each little step isn't that hard, but there's just so many steps. And you have to know a lot of little facts, like where are things positive and negative? Where is inverse cosine even allowed to be? You've got to be in command of a ton of math. What we're doing right now is called trig, right? And did you know that trig was, sit up there, it used to be its own class, like an entire year of trig. Nowadays it's built into pre-calc, and it's about half a year. In our class, we actually shorten it down to, it's just a little more than a quarter. And that means you're learning stuff that kids used to learn in an entire year in a quarter. Now, granted, they went a little further than this back in the day when trig was an entire year. But and why do we go so fast? Because you're in honors. We're going to end this year with 4 units that regular pre-calc won't ever learn. And they're things that are really cool that you just don't see in a normal math class. And when Stanford, I think it was Stanford, was asked, their math department was asked, what would make the ultimate pre-calc class? They said it would be great if they knew how to do polars, which we're doing, and vectors, which we're doing. And it would be great if they had complex numbers, which we'll be doing. And one more thing I can't think of right off the top of my head. Anyway, those, we add these 4 units in, which are the ones that would make you really, really prepared for calculus. So, okay. But that means we go kind of fast. Cosine of some angle equals root 3 over 2. That's your first step as a rewrite. But it's not exactly like when you saw this problem for the first time. Because when you saw this problem for the first time, you could get 2 answers. Why can't we get 2 answers? Because inverse cosine is only allowed from here to here. So that means these are out. And then cosine is only positive here. Because of the all students take calc thing. Cosine's positive down there, but we're not allowed to be down there. So this one's out because cosine would be negative there. So then we had to be in the first quadrant. And then cosine adjacent, hypotenuse, that's a 1. That's just a 30. That's a pi over 6. Done. Okay, except that wasn't the question. That was part of the question. How do you finish the deal, Mr. W? Now that I've done the inside. All right. Do I need to draw a new triangle? No. If the inverse part is on the inside, you have done all the hard work already. And now it's super easy. You just say tangent of that. So what'd you get? All right. TOA, opposite over adjacent, 1 over square root 3. Raise your hand if you had that one right. Awesome. Okay. Now, do you get that at this moment, if this had been like an A, and this had been a B, and this had been a C, you still could have got the tangent of it. It would have just been B over C. Doesn't really matter what those numbers were. So why I say that is you're going to have problems like this. Inverse cosine of 1 over x. And then the tangent of that. I know it's going to kind of blow your mind at first, but you'll still know where you have to draw that triangle. You'll still know two sides of the triangle. You'll still be able to figure out the third side of the triangle. It'll have an x in it, hint. And then you just find the tangent of the triangle you've drawn. Try it. It's a lot like what you just did. And yes, the answer has a bunch of x's in it. Like x squared, square root of x squared minus 1, that kind of stuff. Not a lot of x's in your answer, but give this one a try. It's just different because one of your sides is a variable. Oh, that's the only thing that's different about it. I want to pause while I give that a try. All right, so let's see if you set up this puppy right. First of all, we have this inverse cosine, and I got to figure out where I'm allowed to be on inverse cosine. So I can only be on the top two. These are out because inverse cosine is only allowed up in quadrants 1 and 2. Next, cosine, and now you might be thinking, well, can I draw it in both of them? And the answer is no. But for a little more of a obscure reason. Can you tell if cosine is positive or negative right now? Can you tell if this is positive or negative right now? No, you can't. How about this? Do you remember that I said you could only have one answer to an inverse problem? So we can't have it in both, that's for sure. So where's the place where you could draw it where it would be assured that you would have a positive? Yes. Ah, okay. In this case, now I could have had the x on top, and so I want to use an argument that would work for anything. In this case, you are right. So we couldn't have had the, yes, that's a great argument for this problem. X would have to be positive. But how about this? Would you agree that if I put it in quadrant 1, that you are then going to be forced to have positive numbers and it'll always work? I'm going to pause for a second. So now I've drawn my triangle, and I'm going to do cosine. A rewrite of that is cosine of the angle is 1 over x. Since it's cosine, I know I have two sides. Cosine is what? What over what? Ka, from SOHCAHTOA. Adjacent over hypotenuse. Okay, so if it's adjacent, 1, hypotenuse, x. Who's smart enough to tell me what that side has to be? What do you think? Tell me what to do. Square root of, and you take this squared, x squared, and this squared, which is 1 squared. Just humor me, I'm going to say 1 squared. And then what do I do to them? I subtract them. Very good. Raise your hand if you had that part right. Okay, good. Next, am I done with the question? I've labeled all the sides. That seems like a really good start, but what's the finish? How do I finish this thing? Raise your hand if you know how to finish this thing. What do you think, sir, in the back? All right, so if I'm going to find the tangent, walk me through that. Tangent of this thing would be the what? And therefore, and do I really need to write divide by 1? Because divide by 1 doesn't really do anything. There you go. Raise your hand if you had that one right. Okay, awesome. That's your first one where I didn't give you both sides. Think about it. I gave you one side and then one variable. But yet, almost everybody got it right because it's really not that much different than what we did before. Okay, so let's do one more. I want you to just set this one up for me and show me your triangle. So, I'm going to keep it simpler. This will look strange. Just draw the triangle and label all its sides and put it in the right place. Then, when you've got that, I'd like you to turn your iPad my way and I'll tell you if you're doing it right. But wait, you ask, didn't you just give us only one side? No, what can you do to make that two sides? Because I don't want you to struggle with this for too long. Yes? Put it as an x over 1. Excellent. I'll pause for a second while you draw me that triangle. All right, so How come we ended up here? Well, tell me two places I couldn't have been. Good. And why not? Because inverse cosine isn't allowed down there. All right, next, why didn't I put it here? Would that allow for the possibility of a negative? We don't want that. Remember how we only have one answer to inverse cosine questions? All right, so then cosine is adjacent over hypotenuse, and then this last side, which pretty much everybody had, 1 squared minus x squared, or 1 minus x squared. All right, now the tangent part of it is simple, right? This last piece is so easy. TOA, opposite over adjacent. I'm going to pause for a second. Okay, so let's get right back to it. What else do you need to know? Well, I told you yesterday that I was going to tell you why cosine wasn't allowed here and there. And there's another little piece that's on the test about this. Like, why can cosine, inverse cosine, only be up here or here, but it can't be down here? All right, it comes down to this. If this is 0 and this is pi, and this is pi over 2, do you remember me saying we don't want to call this 3 pi over 2, even though it is, but for for inverse trig, we usually call it negative pi over 2? Here's why. It goes back to what an inverse means. This is important now. Sine, I'm drawing sine from a different perspective, but it's still right. Do you get that's part of the sine graph? Do you get that what I've drawn is part of the sine graph? It goes to a max of what? And the lowest of -1. And I don't know if you can do this, but do you remember where the first peak is on sine? How about this? I'll continue it the rest of the way. We know how it ends, right? What's the ending spot? 2 pi. What's this spot? Pi. So what's this spot got to be? Pi over 2. Okay. Now, why am I cutting off that part of sine? Why am I not using that part of sine? Because that part of sine doesn't have an inverse. What do you need to be able to have an inverse? This is getting kind of deep here, but it has, the first thing is a function. I can tell this is a function because it passes the vertical line test. But do you know how I can tell if something will have an inverse that is a function? If it passes the horizontal line test. All right? If this line here, same deal, will only touch once, then it passes the horizontal line test. This is the only part of sine that's close to the origin that passes both the vertical and horizontal line tests. And therefore, we artificially limit sine to only be between here and here. Because why? Because that means in that area it can have an inverse. An inverse is a reflection across that line y equals x. So therefore, that's what inverse sine looks like. It's a reflection across that line. And do you remember that inverses have the x's and y's get flipped? So what was on the x now becomes the y. And what was on the y-axis now is on the x-axis. Whoa. X became y, y became x. The new graph is the blue one. It's not the red one anymore. All right. Now, I said all of that because I wanted to tell you why. Okay, first of all, would it be reasonable to ask you what is the domain and range of inverse sine? Yes. That's a test question that we could ask you. What's the domain and range of inverse sine? Well, let me give you the easy answer for it. Do you get that inverses, the x and the y flip? So then if I want the domain and range of inverse sine, can't I just know what the domain and range of regular sine are and flip-flop them? All right. But we have to artificially limit our sine to only this part of sine, the red part right there. Because why? Because if you keep going, then it won't pass the horizontal line test, and that part of it, this part, this extra part where it starts going back down again, that part doesn't have an inverse. So sine's only got an inverse between, this might register for some of you now, sine's only got an inverse between pi over 2 and negative pi over 2. Does that sound familiar from this picture where I said inverse sine is only allowed from pi over 2 to what? Negative pi over 2? And inverse sine's only allowed in there? That's why. Inverse sine's only allowed between those two because if I move back to the one I just showed you a second ago, here's where sine is. What did sine go between? It went between 1 and negative 1 and between pi over 2 and what was that spot? Negative pi over 2. That's why we have to limit between negative pi over 2 to pi over 2. All right, so what if I asked you for the domain of inverse cosine? I would start with, okay, well, what's the domain of regular cosine? And that becomes the range. What's the range of regular cosine? And that will become the domain. All right, let's look at cosine for a second. Everybody, sketch me cosine. Let's go back to the basics. What does cosine look like? From 1 to negative 1, right? And this is 2 pi. That's pi. That's pi over 2 and 3 pi over 2. Now I ask you, which part, the part that's closest to 0, of this graph would have an inverse? Well, it has to pass the vertical line test. This passes the vertical line test always. So they were good on that. So then it boils down to what part of this wouldn't pass the horizontal line test? Do you get that I'm going to have to chop it off right here to allow it to pass the horizontal line test? I'm going to put it back now. Do you see why that part, when it's there, means I'm going to fail the horizontal line test? That means that its inverse wouldn't have a function. Wouldn't be a function, sorry. So as soon as it starts turning this corner here, do you get that that means, oh, now it's not going to pass the horizontal line test there. So therefore, do you get, we only want this part of cosine. Now I want you to think, do you get why inverse cosine is only allowed between 0 and pi? Remember that other drawing? Here's inverse cosine, only being allowed here, between 0 and pi. Do you get from this picture why inverse cosine is only allowed between 0, which is right there, and pi? Because that's the only part of the graph that can have an inverse. Okay, and then if I asked you, what is the domain of inverse cosine? I hope you could make this part of your graph and go, okay, the domain of inverse cosine would actually be the range of regular cosine. What's the range of regular cosine? What's the range of regular cosine? -1 to 1. That becomes the domain of inverse cosine. What's the range of inverse cosine? What's the range of inverse cosine? It's really the domain of regular cosine. What's the domain for the part that worked here? What's the domain of that blue graph? 0 to pi. So the domain becomes the range. 0 to pi. Can it be 0? Yeah, it touches at 0, so it's bracket there. Can it be pi? Yeah, it touches there, so it's bracket. What was the domain of inverse cosine? The domain of inverse cosine was actually the range of the original, which was this one, -1 to 1. If you have to, you can just memorize that, power memorize that. But I think it'd be better if you can just draw the graph of it and say, okay, only this part of the graph works. So if he asks me for the range of the inverse, I'll just tell him the domain of the original. All right, last but not least is tangent. Would you sketch what tangent looks like in the first place? If you have forgotten the parent graph, we got to get it back in your head. Kids are famous for forgetting what these parent graphs look like. And that's a big deal. We really need to emphasize that more. In fact, that's going to be on my next top 20. I'm making another top 20. That's the stuff from pre-calc that you really have to know for calculus. One of them is, what's tangent look like? Another one is, what's log look like? Log looks like this, tree blowing over the wind. Remember that one? What's the exponential one look like? Remember that one? Exponential? When you see it, it makes sense, but it's like harder when I just say exponential and you're like, I don't remember. Okay, so what's the one I just asked you to graph? What? Tangent. So I ask you, does tangent, as it stands right now, does it pass both the vertical and the horizontal line tests? Cool. Then it's the only one that we don't have to like artificially stop. You know what I mean? We have the other one we have to like stop doing sine because if you keep going, it's going to mess it up. This one, it just works right off the bat. So then I can say, how about inverse tangent? Inverse tangent's domain or range? Well, and I'm going to take the domain of this one, and it'll make the range of the other one. So here's inverse tan. Inverse tan's domain and range. The domain will come from the range, and the range will come from the domain. So I ask again, this guy, regular tangent, what's its domain and range? What's the domain of regular tangent? Well, it will go forever, but it's really this little chunk that we're considering. The domain is between -pi/2 and regular pi/2. And can it touch there? This is important. Can it touch? No, there's asymptote lines there. It can't touch there, parentheses. And that domain becomes the range of inverse tan. And what's the domain of what's the range of regular tangent? The range of regular tangent. -∞ to ∞. Very good. Can you touch infinities? No, so there's parentheses. And then that means the domain of regular tangent is that it goes forever. And why is that? I'll show you what it looks like. Once I have reversed my x and my y, that's what you get when you reflect across this line. It's kind of a mind bender. Wait a minute, I think I did it wrong. Yeah, I did. Sorry. Like this. Got to kind of almost turn your head sideways, and it kind of looks like tangent again. Does it have a peak at the top and the bottom? Was it limited before? Yeah, it was limited before. The domain becomes range, right? So this would be pi over 2. This would be negative pi over 2. And will it stop going in this direction? No, it's unlimited in that direction. That's why its domain goes forever for inverse tan. Okay. Inverse tan, that was this one. Remember how it didn't touch? Can't be that, can't be that. So inverse tan can only happen from there to there. Why? Because it's from pi over 2 to negative pi over 2. Let's look back at this picture. Do you get it's from negative pi over 2 to pi over 2? That's as far as it can go. Or if you want to look at it here, negative pi over 2 to pi over 2. That's where the domain was originally, becomes the range down here. That's why it's only between there and there. That's why inverse tangent or inverse sine or inverse cosine can only be in these 3 spots. Inverse tan, and it doesn't touch because of the asymptotes. I have it sort of touching now, back it off. And then this one, remember the other one that was from here to here? Which one is this? The red one there. Sine. And last but not least, what goes from here to here? Cosine. All right. Now, that's a lot. I know, that was deep. But I taught you almost everything you need to know for your next test. So what's a typical thing I'd expect you to know? What is the domain and range of inverse cosine? Would you start by graphing inverse cosine? No, that's too hard. But you'd start by graphing cosine, and then you'd think, okay, what part of cosine do I use? I'd like to try to answer that question from scratch. Don't look back at your notes. What's the domain and range of inverse cosine? So start by graphing regular cosine. Figure out what part of it you can use, and that should be able to answer this question. You start by graphing regular cosine. And then hopefully you stopped yourself right about there because you're like, wait a minute, it's not going to pass the what test? Horizontal line test. So you got to stop right there, in fact. And that's as much of cosine as you can use. Because otherwise, it wouldn't pass that horizontal line test. So therefore, it's from 0 to, looks like it's about halfway done. What does that mean? Pi. If you could continued cosine with this part that we don't really want, it would end up at 2 pi, right? So seems logical it stopped at pi. So that means that's the part of cosine that I want. So now if I'm asking you for its domain, what should I really look at? The range of the original, okay, which was from -1 to 1. Did it touch? Yeah, there's no asymptotes. It touches it. And then the range? The range would come from the, I can wait all day, domain of this, which was from 0 to pi. And does it touch? Yes, there's no asymptotes. Okay, what else could I ask you? You know those new ones that I just threw in an X? Let's practice one of those. inverse tan of x, and then I want sine of that. For this kind, I'll keep your life simple. You can just always draw them in quadrant 1, because in quadrant 1 is the one place where you'll know that all your sides will be positive, and we want quadrant 1 is the only place where all 3 inverses always work. Quadrant 1, safe place to draw your triangles. When you have an x as one of your sides, just draw this puppy in quadrant 1. Okay, TOA opposite over, I'm putting it over 1, over adjacent, that side's square root of x squared plus 1. And then I want the sine of that is opposite over hypotenuse, opposite hypotenuse, x over square root of x squared plus 1. Raise your hand if you had that one right. Cool, you know everything. All right, so now, I'll pause for a second, we'll pull up tonight's homework. Quick side note, in the challenge area, we have this root 3 over 3 going on. Do you remember that that's actually just that rationalizing thing happening? What is equal to root 3 over 3 that would make your sides more recognizable? It's been rationalized, which means the denominator used to have a square root in it. What do you think of the square root used to be down there? Okay, I'm glad I mentioned it. Why is this handy? Because you know a triangle that's got a 1 and a square root of 3 in it. You know what I'm talking about? It's the 1, 2, square root of 3 triangle. That's the 30, 60, 90 triangle. But if you would have just seen this, you might not have noticed that that's the same as this. And you'd have tried to label it with a square root of 3 as the, let's see, this is cotangent, so it would be opposite and adjacent sides. One of the sides would have been square root of 3, the other side would have been regular 3. It would actually have all worked out if you'd have just done it all the way out, but you might not have noticed which triangle you had, and therefore that you don't need a calculator to get it. It's probably why it's in the challenge section, but you need to know this because that comes up, and especially in your homework. The other one that comes up a lot, root 2 over 2. Think, use logic. What would be the same as that, but with the root on the bottom? Yep, 1 over root 2. Somebody signed to me. And if I wanted to be sure that I was right, do you know that you can cross multiply fractions, and if they're really equal, their cross products would be equal? 1 times 2 is 2, and the square root of 2 times the square root of 2 is the square root of 4, which is 2. Can I bring one more for food? Yes, you may. Come on. All right. Pausing. Okay, so here's the ones I want you to do for tonight. See how it says day 2? All right. A lot of these are similar to what we just did last night, so that means to me we don't have to do that many of them. How about if we skip the ones on the right side? We'll just do the 2 on the left side. Then, again, this is kind of more of the same, and it makes it seem really complicated from the directions, but all it's trying to say is that you are limited to be in certain places. You're already used to that. You know where you're limited to be. But this page is labeled challenge, which to me means there's probably something more difficult about it that I'm not even noticing. So I'm going to skip over that page, and we'll go to some of these instead. What's different? Ooh, secant? What? Don't forget that once you write that out as a, okay, that 2. And where can that 2 go also? Do you remember that part? 2 is on the outside. Do you know what to do with that? 2? Do you remember what the double angle formulas were? Do you remember like sine of 2 theta? Does that ring a bell? All right, it's related to that, but we don't have time to cover that right now, so that we won't try to mess with the top 2 then. But these 2, they have the x's in them. Remember me doing the ones with the x in them? You should do these 2 because they're just like that. Okay. Now don't freak out if it ever says you know, secant, you just have to go back and make it flip over, and don't use secant, use the sister of it. Okay, but these two aren't going to do that to you. So we'll do these two. I'll talk more about these double angle ones later. And then what else would be reasonable on this page? You're not ready for that one, that's for sure. So we're not doing that one. This one's just scary because it's got this big number in there, but remember it's two sides. I think you should do that one. Do 150. And it's got the word secant in it. It'll make you think about, how do I do that again? Remember that you write it out and then you flip it over, and don't do secant. Do the sister function of it. Flipped. Okay. I think that's enough. That's all I got for you for today. There.